tertiary alcohols can be reacted with concentrated aqueous acid, like HCl, to produce the tertiary alkyl chloride through an SN1 pathway. Primary alcohols can react with concentrated acid, 48% in the case of HBr, 37% in the case of HCl, to produce the corresponding alkyl halides. And some secondary alcohols can also undergo the same SN1 pathway to produce the expected secondary alkyl chloride by an SN1 pathway. But then we found that if there's a branch in the beta position of your secondary alcohol, when this is treated with a concentrated aqueous acid, the product will not be the expected secondary bromide. The product will actually be the tertiary bromide. There's a rearrangement that's going on where the hydrogen that used to be attached to that tertiary carbon in the starting material is now attached to the adjacent position, the 3 position in this case. We need to understand why that's happening. First of all, we know that when hydrogen bromide gas is dissolved in water, because it's a strong acid, we immediately dissociate completely into hydronium ion and bromide ion. So the source of acid for the initial proton transfer is the hydronium ion. And the mechanism will go in the same manner as any of these 3, where the first step is to protonate the alcohol group, which is an equilibrium reaction. An equilibrium constant roughly 1, to convert the alcohol into the alkyl oxonium ion and produce a leaving group that's capable of leaving. Water will now leave in another reversible process to form the secondary carbocation, which, like all carbocations, goes planar. So we have a planar secondary carbocation, and we know that that secondary carbocation is stabilized by hyperconjugation. So if we were to draw a picture of the p orbital that's empty where the positive charge resides, we would show our hyperconjugation with our sigma bonding orbital between an sp3 hybridized orbital on carbon and a 1s orbital on hydrogen, and we would say that electron density is donating to stabilize the electron efficient p orbital in the secondary position. And we've got additional donation coming from sigma bonds on the other adjacent positions. So in this case, we have hyperconjugation from both directions, from the 2 adjacent carbons, stabilizing the secondary carbocation. So since this hydrogen is already interacting with that unfilled p orbital, it doesn't take much for it to notice that if it moved onto that secondary position, the resulting carbocation would be tertiary and thus more stable. So what happens is the pair of electrons that's forming that carbon-hydrogen bond moves over to form a bond to the secondary carbon. We illustrate that with a tilde H, and it's called a hydride shift. The result of that hydride shift is a tertiary carbocation, bromide, to generate this process that is not in equilibrium is this hydride shift. Because once we've gone from the less stable secondary carbocation to the more stable tertiary carbocation, there's no incentive for it to go back, which would be an endothermic reaction. So this movement of the hydride is called a hydride shift, and you notice that the arrow starts at the bond between the carbon and hydrogen and points directly at the carbon that it's going to be attached to. This pair of electrons is now this pair of electrons bonded to that hydrogen. You can't make this stop. Anytime you form a carbocation, you have the potential for groups to shift if a more stable carbocation can result. The process is referred to as carbocation. But as we've seen, it's not the carbocation, they are the electrons. The electrons move, and the carbocation rearranges because of the movement of the hydride with its electrons. So it's a hydride shift that results in a carbocation rearrangement. It would never be correct to start the arrow at the positive charge and try to move the positive charge. Positive charges can't move. Those are electron deficient. Arrows show the movement of electrons. So there's an additional step. Instead of the standard three-step mechanism that we have, step one being protonation, step two being the loss of the leaving group, water, and step three being the attack of the nucleophilic bromide or chloride, we now have an additional step, the hydride shift that takes the less stable secondary carbocation to the more stable tertiary carbocation before we pick that up in step four with the nucleophilic attack. Of course, in the case of the primary substrate, we just have two steps. Protonation, and then nucleophile attacking and kicking out the water in a concerted step. Once you form this tertiary carbocation, we can picture the hyperconjugation. We have a sigma bond here between the hydrogen and 1s orbital. That's the hydrogen we just moved. It's going to donate its electron density to stabilize. And then we have now two additional adjacent atoms. So we have three places where adjacent sigma carbon-hydrogen bonds can donate electron density to stabilize the carbocation. Three hyperchargative interactions stabilizes the carbocation better than two hyperconjugative interactions. You'll notice that in this case I showed all three donating into the same lobe. Here I showed them donating into different lobes. That's not actually relevant because it's a planar intermediate, so these two lobes are equivalent. So we have better hyperconjugation to the tertiary carbocation, and that drives this carbocation rearrangement or hydride shift. And it's not just hydride that can shift. Alkyl groups are also capable of doing hyperconjugation. You can have a carbon-carbon sigma bond donating into an MPP orbital to stabilize it. And if you do, you can have an alkyl group shift, a methyl group or even something larger. So consider a related compound to the one we just saw, but where instead of having a tertiary carbon adjacent to the position where the bond is going to leave from, we have a quaternary carbon. So I haven't changed the structure much. I've just added an additional methyl group here. Mechanistically, you would expect pretty much the same mechanism. Get used to writing this mechanism. Right, step one is protonation. That generates a protonated alcohol, which can act as a leaving group. Step two, the loss of the leaving group. Water. carbocation. And now there's no hydrogen on that adjacent position, but there are 3 methyl groups. And we can have a methyl group move tilde CH3 or tilde R to illustrate that it's an alkyl group rather than a hydrogen. So now a methyl shift. And we will generate a rearranged carbon skeleton, where now the 2 methyl groups are in position 2 and position 3 instead of both on position 2. So we go from 2,2-dimethyl, 3-pentanol, after trapping with our bromide ion step 4. This is step 3. Nuclear heroic attack. Two, 3 dimethyl. Right? Or we come to 4-methyl, 2-bromo, 2,3-dimethyl pentate. The reason this reaction occurs is the same reason the hydride shift occurred. We can stabilize the carbocation by going from a secondary carbocation to a tertiary carbocation. And that results in a greater amount of hyperconjugation to stabilize the carbocation in the MTP orbital in the tertiary position. Carbocation rearrangements then are something we have to watch for, and we expect will be pretty prevalent if there is branching at the beta position when you were to form a secondary carbocation. If the initially formed carbocation is already tertiary, as we saw in the case of the T-butyl alcohol, then there's no reason for it to rearrange, even if a more stable carbocation could form. Although it is possible for one tertiary carbocation to rearrange to another tertiary carbocation and see a rearranged structure, even in the case where the initially formed carbocation is quite stable. In addition to hydride shift and methyl shifts, we can also see changes in ring size. We can see ring contractions if the initial ring is a larger ring than 6, because those are less stable than the 5 and 6 membered rings. And we can see ring expansion if we start with a ring or an unstable cyclobutane or cyclopentane can rearrange to the corresponding cyclopentane or cyclohexane by ring expansion. And we'll see examples of those during the next section, where we'll talk about what happens when you treat alcohols not with concentrated HCl or HBr, but concentrated acids, sulfuric acid, phosphoric acid, things where the counter ion is not a good nucleophile.